Hello and welcome to the 50th, that's right, the 50th episode of PEEPanEIP, an educational video series where we learn about an improvement proposal, upcoming upgrades, and the basics of Ethereum blockchain. I'm Pooja Ranjan, super excited to host this golden episode. Hard to believe it's been over a year since we started. I would like to thank all our guests, panelists, my colleagues at Ethereum Cat Herders, and every individual who contributed in building and sharing these amazing community resources. This has been a phenomenal expedition in learning Ethereum. With that being said, let's continue with today's episode, Upgrading the Beacon Chain, with a very special guest, Paul Hauner. And we have also been joined by Elita Moore and William Schwab. Paul is a developer with Lighthouse, a beacon chain client, and has been actively contributing in the development work on the consensus layer. Merge is the next big change that Ethereum community is planning for. To learn more on the topic, let's welcome Paul. Thanks for joining, Paul.
Hello, Pooja. Thank you. It's great to be here. Excited to be here on your 50th as well.
Right. So before we get into the topic of the day, generally we request our guests to provide a quick introduction, maybe a talk about the professional history, how you joined Ethereum community, etc. And then I suppose you have got a very good presentation to follow up with that.
Oh, I'm supposed to have a presentation ready? That's right, just checking. So my name is Paul. I've been a software developer for professionally and maybe 10, 12 years or something. I originally worked in control systems, so controlling motors and projectors and lights and audiovisual things like this. I got sucked into Ethereum in about 2015, I believe, around the crowd sale time. Had seen Bitcoin before, didn't find it that interesting. We found Ethereum really fascinating. So started getting involved in the Sydney Ethereum meetup community. A couple of my friends were also involved, and we went to DevCon 2 in Shanghai. And then from there started Sigma Prime as a bit of a side hustle. That was about almost 5 years ago now we started Sigma Prime. So since then we started doing a little bit of smart contract security auditing, which the Sigma Prime does a lot of now. Myself personally, not so much. Grew the company through that, and then eventually got involved contributing to the open source Ethereum proof of stake movement. And then yeah, Lighthouse started producing a Rust implementation. Sigma Prime started producing a Rust implementation of the current specifications. Then we called it Lighthouse because it was kind of like a rusty beacon for the Rust and the beacon chain. And then since then, it's grown into a big project with a bunch of maybe order of 10 people on it, many lines of code and many users, many billions of funds staked. So yeah, that's a rough history of me.
How many developers are working on it?
About 10, probably a bit less full time, but order of 10.
It's crazy. You guys are managing billions, and it's 10. It's pretty impressive.
Yeah, I know.
Right, fascinating. I mean, every story is an inspiration for someone here. Well, I appreciate you joining us so early in the morning and want to make the best of it. So without further ado, let's peep in.
Alrighty, I'll just get my presentation started. All right, so let's get started. Today, I'm going to be talking about merging Ethereum. So originally, that was this was kind of billed to be about Altair, but I started talking about the merge, and there's just so much to talk about that I thought I'll just go all with the merge. Plus, Altair's at a point now where in about maybe a bit over 24 hours, the fork's going to happen. So I feel like if we waited 48 hours, we'd have a whole lot more to talk about with Altair. So this one is just about merge. I hope that's okay with everyone. So I think we've seen a little bit about myself already. Sigma Prime is where I work. The whole company is about 20 people. The rest of them are doing information security stuff. So we work very closely with the Ethereum Foundation and also a few other blockchains, Filecoin, other protocols like that on the information security side. So going to be a few parts to this talk. So the first one, I want to give an overview of the merge, just to give people a bit of an idea of what's happening, the mechanics involved. So very, very briefly, the idea is to replace proof of work with proof of stake. There's a few reasons we want to do this. One is the environmental reasons, as my emoji suggested, and the other is for security reasons. I think the Ethereum community in general prefers proof of stake for many, many reasons. So accepting that we want to do it, the way that we're going to do it is via EIP 3675, Upgrade Consensus to Proof of Stake. So this is an EIP by Mikhail, Danny, and Vitalik. There's already been a PEEPanEIP talk about this by Mikhail. It was very, very detailed, very good. He went through the specifications. So I think if you just look in the PEEPanEIP channel, you'll find it in there. So what I'm not going to do is go through that EIP in fine-grained detail. But what I'll do is I'll kind of look at it from a more high-level view and see what it's like for perhaps users and stakers rather than the line by line. So I guess to start, this is a very, very brief summary of what is in EIP 3675. So we have in this image 2 chains, one on the top, one on the bottom. This is what Ethereum is now. So the top chain is proof of work Ethereum. It's what everyone's kind of known as Ethereum. It's been running since 2015 or whenever it started. And it's proof of work, and it's a chain full of basically a little bit of proof of work stuff and a whole bunch of transaction stuff. Then in December 2020, so December last year, we launched the Beacon chain. So then we started another Ethereum chain, and that chain just has staking stuff in it. So it doesn't actually do any transactions. All we do is just manage validators, give them rewards and penalties for being good and bad. So the idea with EIP 3675 is there is a terminal proof of work block so that the chain stops. And then from there, the Beacon chain brings in the transaction stuff into its blocks. And then from then on, it carries on with both staking stuff and transaction stuff. So this is a broad overview of EIP 3675. So that means there's going to be one proof of stake chain to rule them all, does it? Not necessarily, depends how you look at it. So from a broad overview, we do have just one chain. So if you're looking at it from the outside, perhaps from a high level view, you can see that just this one chain inside the blocks is stuff to manage staking and stuff to manage transactions. But if we have a look a little closer inside, we've actually built another chain inside that chain. So these beacon blocks, they're going to have staking stuff. Those blocks reference each other, and then the transaction stuff actually references a chain inside itself. So why did we do this sneaky chain? It's not to hide a pre-mine or anything sinister. It's for, I think, 2 good reasons. So the first good reason is backwards compatibility for existing tooling and dependencies. So Ethereum, as we know it, has been running for many years now, and there's a lot of things that expect there to be this this predictable chain. The kind of chain of blocks that if you look on Etherscan, you'll see, referenced by parent hash. Each block has a root of the state tree, and then there's smart contracts that use the EVM to modify that state tree, and all of these dApps built on top of it. So the idea of maintaining this kind of existing legacy looking, I guess, chain inside the new proof of stake Ethereum is so that we don't break all of this tooling. That'd be very, very painful if we did. So we keep this transaction chain so we can maintain these applications with minimal changes. Second reason is because we already have a whole bunch of software that manages that chain very, very well. So all of the existing Ethereum clients like Guess, Aragon, Nethermind, they all do a great job at managing this very difficult task that is, maintaining this chain over the network, storing the database and syncing it. And also with this reason, we already have a bunch of these consensus clients, Ethereum Beacon Chain clients that do a great job at the proof of stake stuff. So they, count, tens of thousands of attestations a second, and they do a very good job at that. And it's quite difficult to task on its own. So the idea is that if we maintain these separate chains, then we can use the different bits of software to maintain it. So a little bit like this. So with this new chain, we're going to let the existing Ethereum clients like Go Ethereum maintain the transaction stuff so they can keep running with minimal changes. And then we have all of the Beacon Chain clients, they can continue to manage the proof of stake things. So I've been using kind of some pretty loose terminology so far, staking stuff, transaction stuff. Hopefully I haven't offended anyone yet with that, but I wanted to try and introduce a few concepts before we got too heavy into terminology. So now all the stuff that I was calling staking stuff, we're going to start calling the consensus layer. So this is all about coming to agreement on the chain, which chain is the right chain, which blocks should be discarded, validators, how many rewards they get, what they vote on, things like that. So that's all the consensus layer. That's something this is Lighthouse's job, or Prism's job, or Nimbus's job. And then on the other side, we have execution layer. So this is pretty much what current Ethereum is now. It's just all execution layer. So this is Guest, this is Aragon, all these clients. And this, the execution layer is interested in processing transactions, is interested in maintaining the Ethereum state, contract state, balances, preventing double spends and things like this. So we have the consensus layer for the staking stuff, and then the execution layer for transaction stuff. Following this, with this, we also have the same for clients now. So we can call, Lodestar, Nimbus, all of these consensus clients, and then we can call Besu, Nethermind, all of those execution clients. And you can see I'm gonna use these little icons, this little voting ballot box to talk about consensus, and then this little calculator to talk about execution. So that'll be a common theme. So of course, the best type of terminology is competing terminology that has no agreement upon it. So we're kind of in the process of switching to this new consensus execution stuff, but there's still a few players out there that are into S2 and S1. So let's go over them. So the existing terminology we have is F1 and F2. This came about sometime before the Beacon chain launched in December 2020. So I guess prior to 2018 or 2019, we just had Ethereum. Everything was Ethereum. Then in 2018, Vitalik announced the Ethereum 2 specification, and then the Ethereum 2.1 specification. We all forgot about 2.1, just called Ethereum 2. So the idea was that all the proof of stake stuff gets called Ethereum 2. And then kind of by default, we ended up calling present Ethereum 1. So there's been an effort, I think, primarily pushed by the Ethereum researchers to rename these terms, I guess, for two reasons. One, I think it's because they're really interested in keeping Ethereum unified. So they're not quite sure what Ethereum 1 plus Ethereum 2 equals, if it's 3 or 21. And also, I guess these F1 and F2 terms aren't very descriptive in themselves. You can't just look at F2 and know what it's talking about. So the idea was to rename them. S2 becomes consensus, F1 becomes execution. So consensus plus execution equals Ethereum. This is the general idea. So I use the new terminology. I kind of like it because it's a bit more descriptive, and it's also what the specification uses, so it's easy for me if I align with it. But I'm not going to judge you. You do you, call it whatever you like. So a little bit more terminology. So this is the chain that I showed you before, the chain in the chain. So these were blocks that they had staking stuff inside the blocks and then transaction stuff. So what I'm going to do is I'm going to rename these. I didn't rename them, but at least for this slide, I'm going to start using their real names. So the transaction stuff inside the blocks is called execution payloads, and the actual blocks themselves are called beacon blocks. So what we end up after renaming that is we have these beacon blocks, which is the big encapsulating blocks, and then a subsection inside those beacon blocks is an execution payload. So the execution payload contains all the stuff about transactions, smart contracts, existing Ethereum blocks, and the beacon block wraps that and also includes information about proof of stake validators. So just quickly for the, programmers or developers out there, have a quick look at the data structure. So this is a beacon block body. So the body, the meaty part of a beacon block, we can see the first, 9 fields. These are all proof of stake things. And then finally, the bottom one, the execution payload, which is new in the merge. This is where we put all of the execution things. So if we have a look at the definition of an execution payload, it looks very, very much like an existing Ethereum block. So if you were to go on Etherscan, start clicking around on the block, you'd see these fields. Notably, proof of work stuff is missing. So what we've done here is we've basically taken the data structure that is a Ethereum block with all its transactions and gas limits, gas used, and then we've put it inside a beacon block as a field. So we've encapsulated inside the other one. So it's a bit of a long talk. So I've got 3 of these little intermission slides here from Monty Python, if anyone gets the reference. So I'm just taking a minute here just to breathe, maybe open it up to some questions and let people relax. Any questions so far?
One comment. The representation of Ethereum's both layer, the consensus layer and the execution layer, is wonderful. This is something I think that has been missing for a very long time. People are trying to understand what is ETH1, ETH2, and will there be an ETH3? So thank you for that visual presentation.
No worries, glad it helped. Very good. Alrighty, if there's nothing else, I'm going to jump into the next section. It's fairly technical as well. Then we'll have another little intermission, and then we'll do some more kind of less technical stuff, looking at coordination. All right, so I think understanding the relationship between the consensus and execution layer can be highlighted by looking at producing and processing a block. So I'm going to walk through those two stages now. So first, we're going to look at what it's like to produce a beacon block. So let's start with a bit of our setup here. So we have a person, they're on their computer. They happen to be running validator number 42. So inside their computer, which is the dotted box here, they're running two programs. So the execution client and the consensus client. Now, this is necessary for any validator. They must run both of these processes, and those processes are connected to each other via an API, JSON RPC, that the execution client already uses. So this is their computer. They're running two programs. Those programs are talking to each other. Those programs are also pointed at the internet. So we're producing a block, and the first step in that is that the consensus client learns that it's been elected to produce the next block. So it's the consensus client that learns this, because it's the one that's in charge of validators and block proposing schedules and things like this. So first thing it does is it sends a message to the execution client, and it says, please prepare to produce a block. And it does this via the engine fork choice updated method. So it sends this message to the execution client. Then the consensus client doesn't really have a whole lot to do at this point. However, the execution client is starting its algorithm to find the best, most profitable, most efficient set of transactions to include in that block. So this kind of mirrors what happens in proof of work now. Once the execution client, if it's mining, once it receives a block, then it knows it has to try and build a good set of transactions on top of that block. So what it's trying to do now is just taking its time to collect and build a really profitable set of transactions. So the next step is that the consensus client, its slot arrives when it needs to produce the block. So it knows time to produce my block. It's very excited because it's going to get some rewards from that block and get its graffiti in the chain. So what it does is it sends a message to the execution client and says, please send me that execution payload that you've been working on, the one I told you about before. So it uses the engine get payload method to do that. So then at that point, the execution client materializes this execution payload, which is just like a current Ethereum block set of transactions, a state root. It sends that back to the consensus client. So at that point, the consensus client has this full, complete beacon block with the execution payload in it, and the execution client can kind of relax for a little bit now. So the consensus client will then broadcast this entire block to the whole world, so all the other beacon nodes, asking them to include it in their chain. Hopefully it reaches all of them. And then what it'll do is it'll send a message back to the execution client saying that that payload that you gave me, a validator included it in a block and signed across it. And then in fact, that block became the head of the chain. And it uses the engine fork choice updated method to do that. So it doesn't just tell the execution client that because, so it's excited, it learned to, produce a block and it can put a picture of it on the fridge. It does it because the execution client relies upon the consensus client to tell it what the head of the chain is and which blocks are valid from a proof of stake perspective. So just because the execution client produced a valid execution payload, it doesn't actually know that a proof of stake validator selected that payload and included it in the chain. So once the consensus client tells the execution client that this block is valid, it's the head of the chain, then the execution client can perhaps prune some old blocks that it doesn't need anymore, that have been reverted due to finality, and it can persist that that new execution payload on its disk as a canonical payload. So before we move on, what I want to do is just quickly run through this again, just to try and cement it in case anybody missed anything. So we have our setup, nothing's happened yet. Consensus client learns it's time to produce a new block. So it sends a message to the execution client, please prepare to produce a new block. So then consensus client can chill. The execution client is working to produce the block. Now it's time to produce the block. So the consensus client says, please give me that payload that I asked you to prepare. So then the execution payload goes from the execution client back to the consensus client. Consensus client has a full block, it broadcasts that block on the network, and then it tells the execution client that block was included by a proof of stake validator, and it was set as the head of the chain. So what have we learned from this little walkthrough? First thing we've learned is that validators must run an execution layer client and a consensus layer client in order to produce blocks. This is definitely not the case on existing Ethereum. For miners, they didn't even have to touch a consensus client. So anyone that's producing blocks for Ethereum is going to be needing to run both of these things. On the beacon chain side, you did need an execution layer client to produce a block in some circumstances. We always presented it as a hard requirement, but it wasn't necessarily. So now, if you're a beacon chain validator, you absolutely cannot produce a block unless you have a consensus client, an execution client connected to you. So these two services are connected by some sort of RPC API. For example, the HTTP JSON RPC that most of us use to talk with guests and other execution clients already. A consensus client is, in fact, completely unable to produce an execution payload by itself without the execution client. So consensus client like Lighthouse just doesn't have the machinery or the information to produce an execution payload. It can't determine the state route, do anything like that. So they're completely reliant. And on the other side, the execution client relies upon the consensus client to know which chain is canonical. So the execution client just doesn't have any of the proof of stake machinery in it to know who is a validator, what they signed, and what the head of the chain is. So a couple of lessons we've learned with that one. So I'm going to go through the processing of block now. So we're going to look at, I guess, the other side. So we've produced and published a block. Now let's look what it's like for a node to receive that block and verify it. So this setup, we have a generic user here. They might be a staker. They might just be following the chain just for the fun of it, for information gathering purposes. It doesn't matter. Their setup is going to be the same. They have, inside their box here, they're running a consensus client and an execution client. So one thing we know now is that not only do validators have to run these processes, but anyone following the chain has to run both of these processes connected to each other. So we'll start through the example for this one. So the consensus client from the network, it receives this beacon block. It doesn't know whether the execution payload is valid. It also doesn't know whether the beacon node is valid. So the first thing it does, kind of a minor step, is it does very brief validation of some parameters of the block, and then repropagates that block on the network for its peers so they can start processing this block. So after it's done that, it still doesn't know detailed validity information about it. So what it's going to do now is it's going to send a message to the execution client and say, hey, I got this block, and can you please verify this execution payload here? So it's going to use the engine execute payload method to do that. So after that, we've now got both the execution client has its payload to verify, and the consensus client has its beacon block, the consensus properties to verify now. So it'll do a bit of work. Eventually, the execution client in this example determines that this execution payload is valid, and it's going to send that back to the consensus client, who now knows that it has an execution payload that is valid and it can continue validation. So in this example, the consensus client says, yeah, okay, that execution payload was valid and all of the consensus properties of that block were valid. So I'm just going to save that to disk now, persist it in my canonical chain because that is indeed a valid block. And then I'm going to send a message back again to the execution client and say, hey, that payload that I got you to verify before, it's now at the head of the chain. And it uses that engine fork choice updated method to do it. So looking at this again, we've got this two-step process again where we say, hey, execution client, is this payload valid? And then it says, yes, it was. And then that wasn't enough for the execution client. What it also needs to know from us is, okay, that payload was valid, so I could continue to verify the block, and it turned out the whole block was valid. A proof of stake validator approved that. So there you go. It's now canonical, and you can include it in your chain and deal with finality and stuff like this. So we need this two-step kind of phase, remembering that just because the payload is valid doesn't mean that that the beacon block containing it was valid. So before we move on, I'll just do a quick recap of this one again. So have our empty setup again. What happens is the beacon block comes in from the network. We don't know if it's valid. Do some brief validation on it. Then we repropagate it to the rest of the network so everyone can see it. Then the consensus client sends their payload to the execution client for verification. They both are then ready to verify some components of the block in parallel. Then the execution client sends back this payload to the consensus client. So then the consensus client can then complete verification of the block, save that to disk, persist it, and then the execution client, sorry, the consensus client sends a message to the execution client saying, hey, that was valid, you know, update your fork choice. This is the truth of the chain. So now looking at processing a block, what have we learned in this one? So we've learned that all users must run an execution client and a consensus client to verify blocks. So not just stakers. If you want to follow the chain, you want to run a block explorer, you want to do data analytics, you're going to have to run both of those because independently they just don't have the smarts to verify the Ethereum chain anymore. And I repeated this a couple of times, but the execution client needs this second message to verify that the execution payload was accepted by consensus. So, you know, just because we found a valid set of transactions in a state root doesn't mean that they were produced by a valid validator. So just keeping this in mind, it's a two-step process. All right, that was pretty technically heavy. Got an intermission again. So I have a drink. If anyone's got any questions, please go ahead.
When we talk about verifying the execution payload, so that means that that is when every node is kind of running every transaction in the block just to make sure all the transactions are valid, or okay, fine.
Yeah, exactly right.
Mm-hmm. And when we're looking at kind of the consensus verifications, that's kind of more, well, I mean, I guess also in execution and on consensus layer, there's also verification of the headers just to make sure that the hashes match up properly and things like that, like all the other parameters are correct. Or,
yeah, that's right. So from an execution side, we're looking at pretty much exactly the same verification that's happening on Ethereum presently, just minus the proof of work verification. It just trusts the consensus node that if it basically what it says about the chain. And then on the consensus side, we're doing all the stuff where, you know, verifying that it's a chain. We're looking at the assignment of validators, who's the correct validators has signed across it. The validity of other like slashings and messages in there, and also looking at the weight of attestations that have voted on that block and whether or not it should become the head. Is that roughly the answer to the question you're looking for?
Yeah, absolutely. Thanks.
Beautiful.
So I have a question here. You mentioned about if someone wants to run an explorer, they might have to run both the things because it's a two-step process, right? How good or valid it is for a simple user? Do they have to do that the same thing? Like if there is someone trying to be a validator, does he have to have both the nodes, or he can use some third-party services there?
They'll have to run both the nodes. It might be that people come along. So there's like Ethereum Docker, I forget what it's called. There's a bunch of people that have made these Docker kind of wrappers around Ethereum, like Beacon node clients and the current Ethereum clients. So I think that people might build wrappers around it so that it presents as one, like these two processes present as one thing that you can use. But fundamentally, anyone who's going to be validating or following the chain has to run both of these processes.
Makes sense. Yeah. Thank you.
Okay, I just remembered now that I do have more technical stuff. I moved this intermission forward, so there is a little bit more technical stuff, and then we'll go into the organization stuff. So, ready to move on? All right, let's move on. Okay, so let's look at the merge from an infrastructure perspective. So, if you're someone that is running nodes, what's your infrastructure going to look like? So, in the previous examples, we showed roughly this setup. So you've got consensus client talking to the execution client via a JSON RPC. This one is just, you know, between two local machines. They might be talking over HTTP. They might be talking over Unix sockets or whatever. So this is probably the simplest scenario you've got. Like two processes running on the same computer connected via some RPC. This scenario is also very possible. So you got your consensus client on one computer on one side of the world, and you got your execution client perhaps on a server on the other side of the world, and they're connected probably via HTTP over the internet, and they can talk to each other like that. They want to make sure they've got a secure connection, but these two programs can be located anywhere as long as they can speak to each other. We can also do a one-to-many relationship here. So you can have your consensus client, speaking to multiple execution clients. So since the consensus client is kind of driving these execution clients in a way, it can just send out the same messages to all of them, and they all should be able to follow it. There is a bit of an edge case where if one of these execution nodes says that a payload is valid, that the other one says it's invalid, but that would be basically a consensus failure between execution nodes. So that'd be something the consensus client has to handle, but it would be a failure mode. So this kind of layout is possible. Lighthouse now, the merged version supports this. You can connect a consensus client up to multiple execution clients. You might want to do it for a bit of redundancy, and you also might want to do it from, I guess, an academic perspective of just trying to see if they ever disagree. So something we do during testing. So the other side of that is a many-to-one relationship of many consensus nodes driving the one execution client. So this is not something that is currently supported. It's not, I guess, fundamentally impossible. However, the current version of the specification isn't written to really tolerate this very well. And the reason for that is because the consensus node is telling the execution client what the head of the chain is. It's telling it what the shape of the chain looks like. It's actually a subjective view of the network, what the current head of the chain is. So it can be the case that these three consensus layer nodes are all performing perfectly, but due to some geographic network difference, they might actually have different views of the chain. And the execution clients presently aren't really designed to handle the idea of it being bounced around between views of the network. It prefers to have just one view. So this layout for now, not recommended. Maybe we'll get there. I like to think we will, but I wouldn't go down that path at this point. So that brings us to trust, the relationship between these two nodes. So you really need to trust both of these nodes. So if you're a validator, you're running an execution and consensus client, you need to trust both of those. You can't just trust one of them, like a consensus layer node, for instance. So if you have a malicious execution layer node, it tells you which transactions are valid. So it could very much be doing double spend. It could be verifying, rubbish signatures, and it can be just completely ruining the properties of Ethereum state. So on the other hand, if you have a malicious consensus layer node in your system, it can, among other things, censor transactions. So it can just simply choose to not show you certain blocks if it doesn't want you to, and it can go and put you on a minority chain. So you need to be in charge and trusting both of these nodes in this scenario. So now looking at this, I guess, from a firewalling perspective. So if you're going to run these processes on your server and you're wondering how you configure your firewall, then it's just like this. So you have consensus client and execution client running on the same server, and then outgoing from these, talking to the big dumpster fire that is the internet these days. You have just the exact same ports that you would use for the consensus client and the execution client. So you've got discovery ports on UDP, and then I guess RPC communications ports on TCP for both the consensus client and the execution client. So the firewall on that side looks just exactly the same as if you were running those two processes independently. And then on the user side, we have the REST API for the consensus client. So it's serving a JSON HTTP API over TCP probably. And then for the execution client, we have JSON RPC. So it's using the current Ethereum JSON RPC protocols, HTTP, WebSockets, Unix sockets, whatever. So yeah, from a network perspective, it just looks exactly the same as if we were running those two processes separately currently. Same goes to the file system. So they're going to be completely separate processes on the file system. They've got their own databases for putting big chain information in, and also the execution client database, and they'll also store their own cryptographic keys completely separately. So that kind of covers, I guess, hopefully what it looks like from a network and file system perspective. The moral of the story is basically they're just completely separate processes and they run separately and only talk to each other via that RPC. So the next topic I want to talk about is syncing. So anyone that's kind of run Ethereum nodes knows that syncing is kind of the first thing you do. It takes a while. Anyone that's worked on developing knows that this is a very complicated spot. It's a great spot for optimization. So you know, Guess and Aragon, all these implementations have worked for a long time to improve their syncing protocol. So let's have a little bit of look about what we can do. So we looked at that block processing workflow before. And then if you kind of think about, you know, syncing an existing chain from Genesis, then this kind of naive lockstep sync is probably the first thing that you can think would happen. So kind of the first natural syncing idea. This is what we did in the first testnet. So the idea is we get a block, consensus client verifies it, execution client verifies it, then we can move on. We get another block, you know, they both verify it, get another block, it all gets verified. So at this step, we are basically just, you know, every time we get a block, we make sure that everyone agrees on it and then we move on. So this works really well when everything works well, but we have to consider what happens if there's a petition, say something, there's like a network outage between the consensus layer and the execution layer client. So we have this scenario, you know, block 0 comes in, we can verify it, it's great. Block 1 comes in, and then we have, you know, something bad happens, there's a storm, and then for some reason we can't get block 1 verified by the execution client. So then block 2 comes along to the consensus client, it says, yeah, you know, that's great. And then we ask the execution client and it says, you know, I don't know, I can't verify that. It can't possibly verify an execution payload without having the parent, and we didn't give the parent to it. So what we have to do in this scenario is figure out a set of messages for the execution client to say, hey, you know, I don't have the parent, and then we go, okay, well, how far back does it go that you don't have the parent? And then we'll give it the blocks, then it catches up, and then we can give it the same block again. So that's kind of the lockstep sync here. So this process, the consensus layer basically spoon feeds blocks to the execution layer, gives them to it one by one when we know that it wants them. This is very simple to reason about. It's also quite safe. However, the recovery from petition between those two, I guess natively, it could be designed. We're not really clear about what it could be. Might get a little bit complicated. And then compatible with sophisticated sync algorithms. So something to consider as well. Like I said, all these execution clients have been developing these fancy, you know, snap and warp sync methods for quite a while. And they've managed to massively improve the sync speed of current Ethereum. And they do that by not just by downloading blocks faster, but by sending bits of the state across the network. So these complicated schemes, they are very much built around the idea of how things work with proof of work. So you kind of start, if you're an execution client, you start and you might be at the earliest block you have is the Genesis block, but you can see all of these blocks coming in around the head, saying what the latest block is. So you can kind of get an idea of, you know, what the head block is. You can kind of look at the span between the two, and then you can start transferring intelligently bits of the state across and then sync very quickly between these 2 points. So this spoon feeding lockstep sync mode doesn't really keep giving the execution client information about the head, and we're also forced to reverting to feeding it just block by block like this, which is not a good way to sync them, given how far we've come with it now. So during I guess over the last month or so, we've figured out that we probably need to do this thing called an optimistic sync, so that we can support these really nice existing sync mechanisms for the execution client. So the idea with this optimistic sync is that we get the block, consensus layer client verifies it, it goes and talks to the execution client, maybe it verifies it, maybe it can't, doesn't know. In this example, we'll say perhaps it just couldn't reach it, the execution client wasn't synced. So we don't let that stop us. We go ahead and we get the next block, and we import that. Still don't know, we just keep going. and then just we don't know, keep importing blocks, and then eventually execution client figures out it can sync, figures out the span, and then it comes back and then starts approving these blocks after the fact. So we end up with, from the consensus client perspective, it's optimistically syncing, hoping that the execution layer keeps up and marks them as valid. So in this optimistic sync, we now assume that the execution node has, via its own P2P network, can actually get blocks and bits of state from its other peers and then sync to things. So the consensus client just tells it what the latest blocks are, and then it's up to it to get that state and get to a state where it can start verifying blocks at the head of the chain. So this becomes a little bit less simple for reasons I'll go into. However, it's safe as long as we follow a few things I'll get into as well. It natively recovers from these petitions because it allows these spans of unknowns that can be filled in. And it's also compatible with all these sophisticated sync algorithms that Geth and other clients are using now. So it has some really nice properties in that perspective. So we want to look at how to make optimistic sync safe. Then we'll say we're only going to build blocks on fully verified blocks. So we're only going to, when we're making a new block, we're not going to build a type of block if we don't really know whether the parent is valid or not. It's probably possible. It's in some ways it's impossible to do that, but we just have to maintain this idea that we only build the top fully verified blocks because what we really don't want to do is for the beacon chain to keep building blocks where it doesn't know the validity of the execution payload and then finalize an invalid execution payload that could be, a double spend or something like that. That'd be really disastrous. We'd have to do, like a community meat space level intervention to fix that. And along with that, we only ever attest to fully verified blocks. So as validators, we don't vote for the head of the chain unless we know that all of the execution payloads in that chain are valid. So that's how we stay safe in this scenario. So let's look at a little example. So here we have a chain of blocks. So the earliest block, so let's say the Genesis block, is on the left here. So we have that block, and then it has a child of it. It points back to it via a parent root. And then we have a fork in the chain. So we now have one chain up the top with 3 blocks, and we have another chain down the bottom with 2 blocks. So in this scenario, the chain at the bottom has 2 descendants, and they're both fully verified. And then the chain at the top, it has 1 descendant that's fully verified, and then we've got these 2 blocks here where we don't actually know the status of their execution payload. So this chain at the top is optimistically verified. So it's completely valid for us to build blocks at this point. However, it is not valid for us to build blocks here. We probably shouldn't be able to build blocks there, because if we don't know what the payload is, we can't produce a valid successor to it. But for terms of safety, even if we figured out how we could do that, we shouldn't do it because it's unsafe. So in terms of the testing is voting. What validators do, they vote for what they think the head of the chain is. So they could attest to that block, but they shouldn't attest to any of its descendants because they don't actually know whether it is valid chain or not. And then they could, if they wanted to, attest down here. It'd be their fork choice algorithm that tells them where to attest. But what we're trying to show here is that you need to, you can only attest to blocks that are fully verified. So that's optimistic sync in a nutshell. There's a couple of open questions with it. Kind of, they're not major ones. I guess they're kind of subjective things. One is, should we allow a testing or block production if there are any optimistically verified blocks? So that question is, if a node knows that it has incomplete information about the chain, should it be building blocks at all? Because it might just start building blocks of very old things, start creating forks, causing a lot of load on the network when it knows it doesn't have a complete review. So maybe should it just at that point say, yeah, look, I don't know enough to make have a valid opinion here, so I'll just leave that be. That's one of the questions that we haven't quite come to an agreement on yet. And another one is, I guess, a user thing of, should we serve those optimistically verified blocks via the API? So presently, if we're serving blocks over the API, we have this implicit agreement to the user that they're valid, and they can probably action, whatever is in that. But if the block is not fully verified, do we really want to be telling the user about it? So I guess the black and white would be, do we tell them or do we not? And then the in-between would be, maybe do we add a flag to tell them whether it's optimistically verified or not? So these are some of the open questions. They're not showstoppers, they're just the things we're discussing. So at the moment, the discussion about optimistic sync is on a lighthouse issue that I started just to chat internally with the team, but it got a bit broader. So I think that's where the most of this discussion on optimistic sync has happened at the moment. Maybe we eventually will get moved to a different repo or something, but yeah, if you want to check it out and follow on, jump onto that lighthouse issue there. All right, another intermission. So this, I promise, is the end of the technical stuff. So I'll take a sip of my glass of water here and open the floor to questions.
I have a couple of questions. Two questions. I think one is related to optimistic sync. If you can go back to that diagram.
Sure.
So here in this diagram, you mentioned that the attestation should be done to the last valid block, and there are two possibilities to do it. So would there be any algorithm to decide which one will be accepted? Because both would be the valid attestation here, right?
Yeah, that's right. So that'd be our fork choice algorithm that determines which one we should vote on. So what the consensus client would do is it would weigh up the weight of the votes for previous attestations it's seen, and then vote on the one that it thinks everyone else is voting on. If it hasn't seen anyone else vote, it takes kind of like an arbitrary thing. But yeah, definitely an algorithm to choose which one of those possible targets it should vote on. And that algorithm is standardized between clients and tested and stuff like this.
And is this fork choice feature that we are discussing going in with the Altair, or something that we can expect in later upgrade?
Fork choice already exists, and I think it'll stay. So it's been used since Genesis. Very important part of Beacon Chain, and I don't think that, apart from being aware of this optimistic thing, I don't think it's going to change at all for the merge. There's a couple of little changes we want to make to fork choice, but nothing that's related to merge. So yeah, that algorithm already exists, already in production. It doesn't need any changes really to support this.
Yeah, I know. I was aware that it is into the production. I was just trying to understand, in this particular situation, is this being documented there? It's already documented, or something that we would want to do it with the merge?
Oh yeah, sure. Yeah, so the idea, so the fork choice now it just has blocks and they're all fully verified. If they're not fully verified, they're not in the tree. We would need to modify it to support partially verified blocks, but it wouldn't change the specification, I don't think. It would just change the implementation. So that's something I'm going to do in the next couple of weeks, change our implementation to have this idea that it should stop when it's doing a test testing or building, it should stop at the fully verified block. But something I didn't mention is fork choice also needs to know, other parts of the consensus client need to know about the unverified tips as well, because what it wants to be doing, although it's not testing or building blocks for those unverified blocks, it should be trying to ask its peers for descendants of those blocks. So consensus client has to have this idea of what it can attest, what's safe, and then what's optimistic in terms of what it should keep building on.
Makes sense. Okay, I have a question. Maybe we can go one slide earlier.
Yeah.
Here, do we expect some kind of lag here in like syncing, in this kind of, if we want to continue with this syncing mechanism?
Yeah, we can expect some lag. So I think what will happen is, so the execution layer can't get ahead of the consensus client really at this stage, but the consensus client can definitely get ahead. So what we'd probably see is the consensus client sync fairly quickly to the head, and then have to spend some time waiting for the execution node to catch up, because the execution node is actually, its sync is much more burdensome, much more heavy than consensus client. So we'll probably see, it catch up. Your consensus node will probably say, I'm at the head, but I'm still waiting for my execution layer to sync up. I'm still optimistically synced, and it'll catch up, and then you'll probably get a notification saying, okay, both of your clients are ready to go, and you're good to go.
So this lag, is it significant enough to give opportunity for double spending, or is it like really low and that's the minimal possibility of getting double spending?
Well, the lag is, it will be significant. It'll be a matter of hours or days, however long it takes to sync an execution client. But as long as we maintain these safety properties, or we don't build blocks atop it, and we don't serve that information to users as if it's the truth, then we stay safe. So when the consensus client, we can think of both as together. So we'll just say that if they're not both synced, then you're not synced. And then from that perspective, we maintain the existing guarantees. So if someone has a non-synced execution node, they wouldn't trust it anyway. I mean, that's not true. They could trust it to the point where it's up to. So we do bring in this idea that if you're the beacon node, you might be off on an optimistic branch that's invalid, and you could query it and get in an invalid state. But yeah, like I said, as long as we mark to the user, we're clear to the user that an optimistic synced block is not a real block, then we're safe from double spends.
All right, that's interesting. So I have just one last question about the communication tool. You mentioned about JSON RPC and REST API. I suppose there was some discussion going on whether the execution client should continue with JSON RPC and this one should have REST API or should have the common one. Is there any decision on that part? Like we'll be using different for different clients?
I haven't heard on that actually. I know that Peter from Guess is regrets choosing JSON RPC for the execution client, but I'm not sure. I also haven't been following this because I'm in a bit of a consensus world. I haven't been following how that's been going to change it to REST. My understanding, I guess, was that we're pretty far down that path. It'd be hard to change, but yeah, if they're open to change, I'm open to it. So I guess my best answer there is I don't know. I'm sorry.
Oh, no worries. Till there is any official announcement for that, good that we have every options over there, the HTTP, WS, etc. So we'll keep on with that. Thank you so much.
No worries.
I guess on a similar note to that, right now you mentioned that the communication between the consensus layer and the execution layer is itself, I believe, JSON RPC.
Correct.
Do you think that we'll see kind of like 2-in-1 clients? Or is that actually like spec'd out that there must be 2 separate clients that communicate with each other?
Yeah, 2-in-1 clients is a great question, actually. So I think I mentioned before about the idea of wrapping the two together into present as one bundle. So that's not really a question. What you're asking is like, because it's kind of one process that'll do both. I'm not sure about this. So on the one side, it would be really nice if you didn't have to run 2 processes. So it'd be cool if, like, say, Teku and Bezu, for instance, both run by consensus. They're both Java. I'm sure you could probably glue them together and present them as one thing. So that'd be great from a simplicity perspective. But one other thing we have to think about is client diversity as well. So if you have a scenario where you have like a majority client, say Prism, for instance, decides to glue itself to Guess, which is also the majority client on that side, then we're kind of going to double this effect where we just have this Prism Guess network. So this is the kind of thing, I guess this is the opposite side of gluing them together, is the ability to have a diversity there between the two. So yeah, if we were to look at just what is easier for users, I would say that they're probably going to glue each other together. But then if we look at the drives behind client diversity, which I think is very strong, then there's going to be incentives for clients not to glue each other together. So from Lighthouse, where I work, that was something I was considering earlier, was gluing together, but I think for client diversity reasons, probably not going to glue each other together at the binary level, and just allow people to build packages that can glue it together to the user perspective, but in a way that they can pick and choose between their implementations.
Very interesting, thanks.
No worries. All right, so let's get out of the technical weeds and talk a little bit about progress, people meeting in person, timelines and stuff like that. So if we want to talk about progress on the merge, we really have to talk about the Amphora workshop. So people might have seen this happening on Twitter. So just to be clear, I only participated in it remotely. I really wanted to be there. These people are my friends, but I couldn't because I'm in Australia and our borders are pretty tight at the moment with good old COVID. So this event, it's called Amphora. It was in Greece. It was a face-to-face event. So the idea was to get execution, client developers and researchers, other people as well, into the same physical space, so they can sit side by side and hack together on testnets. They can get to know each other, and also kind of form some relationships that we're going to need from post-merge Ethereum. So execution Ethereum and consensus Ethereum have been separate for a while, and it's good to be able to put a name to some GitHub handles. Sometimes really helps with communications. I'm sure that while they were there, they didn't go swimming and do anything fun like that whilst I wasn't there. It would have been pretty horrible to me, so I don't think they did that. So the ultimate goal of this event was to create a multi-client merge devnet. So that's a testnet that presents itself to be after the merge. So it has consensus and staking stuff blocks, and to be multi-client so that as many clients are interoping in it together to produce something that looks broadly like what we'll have in mainnet. So multi-client now comes with significant complexity. So we have a bit of an n-squared problem here for programmers out there. So when we say multi-client, that means that Lodestar needs to be able to talk to Pithos, never mind Aragon, Ethereum.js, and Go Ethereum, and conversely. So we have all these nodes linking all of these things. We need to test all of these different compatibilities between these clients. So that was one of the challenges of the workshop, and also of Ethereum moving forward, is to maintain all of these different compatibilities. But that is also a strength of Ethereum. So also you can see the complexity we have here. We also have this scenario where you can imagine that if, say, Lighthouse stops working with Aragon, we still have a whole lot more options in terms of that setup. Or if, say, Lighthouse completely dies, which shouldn't, we still have a whole bunch of other clients that we can work with. So yeah, complexity here that you can see, but hopefully you can also see this this resilience that we have between these two networks. So between these two types of clients and multiple implementations of clients. So we didn't just jump straight into the big fancy mesh. We had some milestones with this event, clearly laid out by Danny and Tim. So milestone 0 was basically just start working in this workshop. Everyone did that before they got to Greece. M1 was we all implement our relative specifications, and then we get the test vectors passing. So yeah, so M1 was also met by most people before they got to Greece. Just irons out, test vectors help iron out any obvious stupid mistakes that we make. Milestone 2 was a one-to-one interop between an execution client and a consensus client. So that'd be, say, Lighthouse and Guest talking together, building a chain together. And that was without the merge transition. So with blockchains, doing upgrades, consensus changes, it's complicated. So the first networks we did, we just said, let's just assume that the merge happened at Genesis, and we're only going to build merge blocks. And then so M3 is the same client layout, Guess Lighthouse, whatever. But then we do go through, so we start without the merge, and then we do the merge forks, and then we bring in the terminal block, and then we roll like this. So once we all figured out that we can do the merge transition with each other, so it's like, from Lighthouse perspective, we do M2 and M3 we do them with all of the consensus, Guess, Aragon, Pithos, and make sure that we can do the build chains with them. And then M4 is kind of bring a few more people into the mix, maybe have a few different consensus, a few different execution clients, start to build these really short-lived local test nets. And then M5 is the all-to-all persistent devnet, where everyone can talk to everyone. I guess the ultimate goal of it. So this is how people track progress. There was a HackMD, big grid. When you manage to interop, you add a link to instructions to do it, and then also show everyone how good you've done. Get a gold star by the teacher. So the event was very successful. One thing it did produce a lot of was tweets of people's terminals. So if you were a part of, I guess, Ethereum client Twitter at that point, then you would have seen a lot of these. Everyone getting really excited about, white text on black background. But the things behind those are actually really cool. So everyone was really, really excited to see these clients building these chains that we've been working to for so long. And throughout the day, just every day, there were just more and more milestones. So it was very, very, very successful, very good vibe there. At least the vibe that I got via Telegram from the other side of the world here. And we did ultimately meet the goal. So we did produce a multi-client, longish standing testnet. So this is Parry from the ES. He does DevOps and other stuff there. So he's tweeting saying that we started this testnet called Pithos. That there's a block explorer. If you want to go to that link, just type HTTPS in front of it. And then there's some instructions there on how to join that testnet. The instructions he's given are kind of for DevOps people. At the bottom, I've given this link, which is a coin cashew guide, which shows just anyone how to join Pithos. So there's a bunch of people running it now. Bunch of teams finding out bugs, people playing with it, transferring apps to each other, doing transactions. So it was pretty cool. The event did achieve what it set out to achieve. Then also this tweet from Marius from the guest team was pretty exciting as well. So he's thanking everyone for organizing it, and he says that he thinks it brought them at least 3 months closer to the merge in just 1 week. So this workshop in Greece was a big milestone event for merge progress, and it set us on a great trajectory towards getting this thing done. So my last slide here, looking at the engineering standing of the merge. So presently we have this public multi-client testnet running at Pithos. I was talking about before. Anyone can join it. We only have one major client that's not yet on Pithos. It's Aragon. I'm sure they have great reason for it. I think they're busy kind of spinning up their client, and they're definitely not holding up anyone. So I think they can more than comfortable to take their time, do it when they're ready. The downstream tooling for the merge stuff is still a bit immature. So the clients are pretty much ready in a very liberal sense. But things like block explorers, for instance. So we have the beacon chain, the beacon with a dot between the A and the IN, the block explorer. They have a great execution, like a current Ethereum explorer. And then they also have a great consensus explorer. I think this is really good. They've kind of built a rough kind of merge together of the two, so we can explore Pithos, but the linking between the two isn't super glossy. And I think there's a lot of other tooling that we haven't thought about yet that needs to develop. So that's completely expected. That the clients need to get there first before downstream tooling can. So that's something that we need to happen before we can look at merging mainnet. The specification requires another round of iteration, nothing major, just some lessons learned from the current testnet, some things we've realized. So the idea at present is to do another round of iteration on the specification and then start some new devnets in late October or early November. And the next round of specification is dubbed to be very, very close to what we'll do in production. So I know people definitely want to hear timelines, what we expect. So I think I'm thinking the first half of next year for a mainnet merge. I think at this point the Ethereum, the clients are pretty close. We're not quite there yet, but we're quite close. But I think that something we probably need to see before we go to mainnet is seeing long-lived testnets running for perhaps a matter of months, just so that things like SSScan, big things like Sushi, Uniswap can start running on this in this new merge environment and see how things work for them. Some of the things I haven't mentioned here are that there's going to be slight changes to the EVM in terms of randomness, and some of the things that we were expecting to get from proof of work have changed slightly. So we do need to make some very hopefully edge casey breaking things in smart contracts. So yeah, I think that I guess in terms of engineering, we're pretty close, but in terms of the community getting their eyes and hands on this, we've still got a bit of time. I don't really know how long it'll take. So that's why I'm kind of shooting it into early next year sometime. Yeah, and that's it for me for this presentation. I'm happy to open it to some questions. I might end this presentation and go back to full screen.
Awesome. Thank you so much. It was really amazing. I mean, I was literally into your presentation the whole time. And I hope that people who have been trying to understand this merge would be like, now they would have very good idea of that. Thank you so much for this.
You're welcome. No worries. I like to use the emojis. I feel like using all these emojis, I feel like how my parents feel when they first discovered clip art. So hopefully the generation under me doesn't think I'm lame. We'll see.
No, it was really interesting. So I have one question on the merge testnet. I think it's related to Amphora. So first of all, I would agree that Amphora, the merge interop event in Greece, was a big milestone towards the big change that we are expecting. And I assume that a lot has happened in this covert operation with multiple combination of EL and CL clients over there. So what does the interop between two CL clients mean here? Like I was looking into this, the client tracker that was shared for registering the milestone for that. So if I look into that, Lighthouse in M4 is interacting with Geth, Lodestar, Besu, another mine. So I understand the picture that you have explained earlier, CS to EL and EL to CS. What is this about CS to CS?
Oh yeah, good question. I meant to mention that during that diagram. Well done, you picked up on it. So that big, I guess, mesh diagram I showed did miss out the interop between the consensus and execution clients because they also need to interop with each other. So that's kind of what so the consensus side has been interoping with each other since before mainnet, and the consensus side as well. So this is just basically like on the beacon chain, all of the different clients interoping with each other, speaking over the network, sharing blocks, and then also the same thing to the execution side. So it's definitely something that is complicated, but it's something we've been doing for a while now. So it's generally a little bit easier for us interoping between our own kind, if you will, rather than with the others. So that interop means between, say, Lodestar and Lighthouse means that peering on our peer-to-peer network and then sending blocks, verifying them, agreeing on the roots of things, the hashes of things, and yeah, generally being kind to each other in that way.
Interesting. I have one more question on the post that you shared, I mean the GitHub link that you shared about optimistic post-merge sync. In that piece, you have mentioned at one place, like there are some uncertainties that CL clients are dealing with. I'm just trying to understand what is the proposed way forward, if there is any.
Oh yeah, for the unknowns.
Right.
I think so. In that comment, there's some talk between, I think Danny talks a bit about what he thinks is safe and unsafe in there. I think we're not super far forward. I think so in terms of building, should we build blocks atop? So there's two questions. There's one is, should we attest or build any blocks if we have any uncertainty? I think leaning towards safety there, probably say no. But it is kind of up to each execution client to determine what they want to do there. So it's not necessarily a strict requirement of the protocol that we have to decide on. We kind of have this wiggle room for people to go their own way. So I think it would probably be, in terms of the way forward there, it'd probably be something like determining whether all the clients agree that we should just take the simplest method. And if they do, that'll be an easy solution. If it turns out you can go either way and people have differing views, I think that we'll just go either way and we won't all agree on it. And that would be totally fine as well. I mean, that's why we have a diversity and not a dictatorship, so that we can experiment with different things. Then when it comes to the API one, that one is, I think, so there's kind of, when it comes to decisions in the client, there's kind of like these core decisions, like the first one I spoke about, which tend to be decided by, I guess, a group of very close to the client developers and some of the researchers, and they just kind of decide on those things because they're the only ones that are interested enough and I guess informed enough to make decisions about them. And then when it comes to the API, there's a bit of a broader circle of people who get involved. which is great because the people very close to the client, we don't really, it's hard for us to think about what users want. We just think about, what is the most efficient thing for our database and what makes sense to us. So when it comes to that API one, I think we'll have to open it to a bit of a broader field, maybe take it to the Beacon APIs discussion. And I think, to there to discuss about what people think. And I think the choice is we absolutely can't serve optimistic or non-optimistic blocks as the same thing. That's just completely unsafe. I think the question is do we serve them at all? Do we serve them with a flag to indicate they're safe or not, or do we just simply not serve them at all? I would lean towards not serving them to all, just because it's the safest thing. But it might be that once we open this up to like some broader participants, that they say, no, actually, in my system, that optimistic block is very important to this reason. So then we'll say, oh, okay, well, yeah, good point. Let's open it up. So I think that's kind of the way forward we have on those two big unanswered questions.
Interesting. And historically, we have seen the wrong term. The consensus layer client teams are really good in like coming to a conclusion real soon, maybe discussing it async and in some of the consensus layer meeting, the implementers meeting that goes on. Well, I know that there is a lot to unpack on the merge, but unfortunately, it's time to wrap up. Just want to check with the panel if you have any other final question, comment, or thought.
Yeah, I just have one, hopefully short. Is there any concern about the proposed like delivery date in terms of its like fallibility, or like whether or not you'll actually make the proposed time?
Do you mean the proposed times is in the ones that I mentioned, or are there some others?
Yeah, that you mentioned. I think it was 3 months or something.
Yeah, well, I mean, I guess in software engineering, especially in this distributed Ethereum stuff, there's always uncertainty about the time zones the time frames that we won't meet them. But I think that there is a lot of pressure coming from various places. One from the Ethereum Foundation research team. So we know Justin Drake, for instance, is applying pressure to make it happen, and he has a lot of levers. He's a smart guy, so I think he'll be a driving force in it. We also have to be concerned about giving miners too long. So if we delay this for too long, then we give time for unhappiness to breed and strategies to counter it happen. So there are a fair few things pushing us towards it, and I think it's achievable. So that gives me a higher, I guess, degree of hope that it's going to happen early next year.
Thank you.
Thank you. So that's all. But before we go, we have got one announcement to be made. Please take it away, William Shaw.
Yeah, sure. Thanks. So we're excited to announce that due to the success of the PEEPanEIP series thus far, we're interested in expanding the initiative a little bit, and we're looking to branch off into a podcast spin-off of PEEPanEIP. We're looking to do long-form technical interviews with different people in the ecosystem on different technical topics, not necessarily just around kind of the infrastructure and EIP structure that served PEEPanEIP so well. And so keep posted. We're looking to try and start that probably within the next coming weeks. So keep your eyes peeled.
Awesome. Thank you, William. Thanks once again, Paul, to talk about one of the biggest change that need a lot of development coordination and lot of education. I hope more users join the stakers community, the Ethereum chain, and help contribute to the ideal ecosystem that we are looking for. For people who missed, we have recorded an episode on EIP 3675, as Paul mentioned in his presentation, with Mikhail Kalanin. The recording is available on ECH YouTube, and we are also trying to get Pithos to explain about the Pithos devnet. I hope we can have him somewhere in December, because in October, November, there are work to be done. So once that is done, we'll try to have him here. A huge thank you to all our YouTube viewers for watching PEEPanEIP, and I hope you all enjoy this golden episode, not because just it was the 50th one, but because it brings us a lot of information on one of the biggest change. Hopefully the information shared today will help many of the questions. If you still have any question, please do share with us on Twitter, Discord, or just leave a comment. You may find the contact of the guest and the list of relevant resources in the description box. If you like this talk, please hit like and share it with the community. Subscribe to Ethereum Catalyst YouTube channel for meeting and educational resources for Ethereum blockchain. We'll be back with another interesting topic for you. Till then, keep watching, keep sharing your love with Ethereum Catalyst. See you soon. Have a good one.